Introduce Scott Budden, founder and partner at Orchard Point Oyster Company.
Thank you, Tanner, and thanks for having me today. Welcome, everyone. Welcome to panel 2. Put together just some slides here to kind of set the context for monitoring and maybe where we're going with that as it relates specifically to kind of the realm I'm familiar with, which is aquaculture, oyster farming, industry, that kind of thing. So this first slide here is actually a picture of our farm from the air. We raise oysters on the eastern shore of Maryland, both in the Chester River as well as Eastern Bay. And this is one of our chief grout sites. We primarily raise oysters on the surface of the water column. This was taken by a family friend from a plain, small, simple crop. So you may be talking about 500 feet up right in this picture. And it's kind of interesting because I know we still use planes to do flyovers for SAD monitoring in the bay. And it just seems we're kind of at this, watershed moment, for lack of a better term, where we can take science, we can take data, and we can deliver sort of tangible, usable results to growers. Whether it be from plane or whether it's, literally you're talking about water quality on your lease. So I put that up there to kind of show some scale. You go to the next slide, please. So here we have a couple more pictures. The one on the left is a farm down in Eastern Shore, Virginia. They're actually a COA partner, Lambert Shellfish. Hopefully they're on the Zoom call. But I know they were undergoing a study with oyster farming gear as well as SAD and how they interact, relate, because there's some regulations out there. I can speak to the Maryland side that directly address that. So they were very proactive with actually taking a look, I think this past growing season, at what is the relationship between shading, gear, SAD, that sort of thing. And then the picture on the right needs no introduction. That's the bay from space. So again, I put that up there. It's trying the NASA satellite to show, we're talking about a lot of opportunities, but a very dynamic environment. It differs from lease to lease. We find within one watershed, and we're talking about, quite a vast area. So there's a lot of opportunity here. I think everybody in the room realizes the importance of data and monitoring off in the scientific academic community, but I think there's a lot of opportunity. And I don't want to speak just to the aquaculture bit, but that's kind of where I'm from. To make that relevant for decision making. Right, next one, please. So on this slide, there's a tracker or some piece of software on the left, and then we've got some underwater footage of restored leaves, so restoration. So I think the opportunity, especially with the industry side, is putting data out there in a way that's usable and tangible to the user. I think farming is challenging, and I don't want to speak for every person in industry, but a lot of times there's, I think, some dose of skepticism with data, right? There's anecdotal stories that people tend to trust more, I think, sometimes, especially coming from a maybe more traditional fishery making transition into aquaculture. So I think it's important in terms of thinking about who is the data for, what is it for, how is it being used. I know we're not at the Q&A section quite yet, but that might be some questions to keep in mind as the panelists start to get to the presentations. What's the data we're talking about, who's going to use it, and why is it important? Next one, please. So, end of the day, why is it important? Why is it important for, say, an oyster farm to have good data, have usable data? It's a very challenging business. I've been doing it for about 10 years, give or take. And I still haven't figured out supply and demand, and I have an economics degree. So I can speak from firsthand experience. It's tough. It's tough to know, predict expected yield. It's tough to know when things are going to be ready to sell. The demand side, that's a little bit out of our hands to a degree because it's market-based. But on the supply side, I think there's a lot of opportunities there for data to help inform decision making. Decisions on the farm that we already talked about, but also factors out of our control, because it is farming at the end of the day. I do farm tours for people that are land ag farmers, and I tell them that exact thing, and they're like, "Well, welcome to being a farmer. We can't figure it out either." But if you think about it to a degree, the static or the soil is a bit more static than, say, the water. It's a dynamic environment. You got things moving in and out. With the soil, you've got what your nutrient loading is, what's in it to a degree, so you can make good decisions. But you're talking about a very dynamic environment here. And so there's a picture on the right here of some HABs, harmful algal blooms, I believe. And I don't think it's the bay necessarily, but it's just some stock photo I took. But point being is that the more accessible the data, the more usable it is, I think the more impact. And so it's important. And, we're talking about this now. Tomorrow's technically like the last day of February season in Maryland, right? And now we have a hurricane right on our doorstep that's going to dump several inches of rain. So, we're talking about going from looking at one thing, and now we're going to be looking at bacteria counts very close into the state is the next, 5 days or so. So it's very challenging. It's very dynamic. How do we get the data in people's hands, and how do they use that to make better decisions? Oops. Go to the next one, please. And this is the last one. It kind of just sums it all up. I don't think any of these little subtitles here are really groundbreaking, but who's it for? What's it for? How can we use it to make better business decisions, make better regulatory decisions, and then also effective policy as a result of all that. So without further ado, hopefully the panelists here can shed some light into that. We have Matt Ogburn from the Smithsonian Environmental Research Center. He's going to be talking about Chesapeake reefs. I guess we'll start with that one.
Thank you very much. So I want to sort of build on some of the comments that we've started out with here about how we can use data and information to learn more about oyster reefs and the oysters and other species living on them. That's really my interest in some of this line of research is, how can we go to a place like Carter's Creek out here outside the window of the room that we're in here, and a place that you can't really see through the water very well. We can't see what the bottom is. You can't send scuba divers down there to easily monitor things because of the poor water clarity. How can we use technology to help understand what's going on the reefs with the oysters and other species on them better? And hopefully use that information, some of which might be incredibly detailed information that we're using as scientists to understand how the ecosystem works, other things that I hope will be simple, low-cost, actionable kinds of information that aquaculture growers, oyster managers, and other people can use. So I'll share a few examples of that. Next slide. So one of the things that we've been doing is underwater video. Again, the water is not clear everywhere in Chesapeake Bay. It's not very clear in most places, but we've been able to see in most parts of Chesapeake Bay enough water clarity on the oyster reefs to really tell us something about what's going on there. So I demonstrated this yesterday on one of the field trips, and I'll show one of the pictures that we collected yesterday at a reef here in Carter's Creek. But basically, we're using GoPro cameras, like a lot of people have, putting them on a frame, sticking them on the bottom, taking some video, and then using that information. Next slide. So here's an example from the main stem Rappahannock River that we collected in 2020, I think. In this one, you can see kind of on the left-hand side, some oysters sticking up. There's some red-bearded sponge in there, some other things going on. Again, the water clarity is not perfect, but you can see a lot going on in this picture, and there's really useful information in there. Next slide. This is the one from Carter's Creek yesterday. So you can see a bunch of oysters on the bottom. I told people, I promise there's oysters down there. I can feel them with the acre. So this is photographic proof that they're down there. And in this photo, you can see that they're covering pretty much all the bottom that you can see. So it's really high cover oysters down there. They're also kind of laying flat, a lot of them. So there's not a huge amount of vertical structure to it. Next slide. And that's the kind of information we've been using to generate data from photos like this, using this very simple qualitative rating system where a photo gets a score of a 0 if there's no oyster at all, a 1 if there's a few oysters, but it's less than 50% of the bottom covered, a 2 if it's more than 50% of the bottom, but there's not a lot of vertical structure to it. I would probably score that Carter's Creek one a 2. And then a 3, it's more than 50% of the bottom covered, and there's a lot of vertical structure to those oysters, with oysters growing on top of each other, so that the vertical height of the oysters above the sediment is more than one oyster. So we've been deploying this rating scale in a bunch of different places. Next slide. And this is an example from Harris Creek and Broad Creek in the Choptank River. Harris Creek was the first completed large-scale restoration as part of the 10 tributary goal of the Chesapeake Bay program. And it's a little bit hard to read the titles for the people in the room, so I'll go across them. The left one is restored sanctuary reefs, and about 75 to 80% of those scored the highest habitat score. So the places that we went to that were restored were still looking really good. These data were from 2017, which was at least 2 to 3 years after the restoration was completed. The unrestored reefs in the sanctuaries did not look the same. So restoration was really critical to improve the structure of the reefs and density of oysters and other things, as you know. And then I've really been interested in looking at harvest areas as well. I've done a few aquaculture sites, but that's something I'd really like to expand into more. But here, this shows that the harvest sites, some of them, whether they're hand-tog sites within Broad Creek or power dredge sites on the outside of it, we're seeing more of the stores of 2. So there are lots of oysters there on the bottom, like we saw here in Carter's Creek, but just without a lot of that vertical structure. Next slide. So photos are one tool that we're using. We're also doing, and I was showing this yesterday too, a very high resolution sonar that's called ARIS. Please don't ask me what that stands for. I'll have to look it up later. I always forget. But there's a picture of it on the left on a metal frame, and on the right is the image you see. It's basically a super high resolution fish finder if you have one on your fishing boat. If you could click the video, it should hopefully play here. We got lucky going over this oyster reef in Harris Creek when a couple of Caretti rays swam through. So this gives you an idea of what kind of thing the video can show. We're using this to study the reef, but especially a lot of the fish that are on the reef, how big they are, what species they are, when you can tell that, like with these guys, how abundant they are. So it's giving us a lot of information that we wouldn't otherwise have. Next slide. So if you play this one's darker and harder to see, but if you look at the top, you'll see a fish swim across, hopefully. A little, it might be a little too bright in the room. Well, trust me, it's there. There's a fish that's about 12 inches long that swims across. So we recorded this video in Carter's Creek yesterday as well. You won't be able to see it unless I show you it on my computer screen, but there's also a blue crab that's walking around in there. So we did see some stuff out there. But this is a tool that we're using to find out a lot more information. Next slide. So we can see different bottom types with it, whether it's a dredge site with really flat shell and some sand in the middle, a spout and shell restoration site, or a stone reef. So we can see differences in the amount of structure on the bottom. Next slide. We can see differences in the size distribution of fish. So this is from an intern's work this summer, where we're seeing more large fish that's on the most structured restoration sites, which is increasing the size distribution of fish. Next slide. And then the last tool I'll just briefly mention here is that we're trying to, the sonar is great. You can see abundance and size. It's hard to tell what species they are. Environmental DNA is a tool that helps you tell what species are out there on the reef. So with this method, we're basically taking a sample of water, getting the DNA out of it, sequencing all of that DNA, and then comparing it to a reference database to tell us what species are there. So this water sample is actually from the oyster reef. These data are from a ground up striped bass stomach, but it's the same basic idea where you can get all of this really detailed information on what's in the water from the DNA that's there. Next slide. So just to wrap up here, we're doing a lot of research. I find that exciting. I think there's some practical stuff from it as well, but we're also really trying to share what we're learning in a way that people can use it and help provide feedback on how they might use things like the photos that we're taking. So today we're launching this Chesapeake Reef story map. If you go to my lab website there, you can check it out on your own. Please, everyone in the room, don't do this right now. We probably don't have the internet bandwidth for you all to do this right now. But this is what the title page looks like. Next slide. One of the really cool things in here that Julie Licky, who was a Chesapeake Conservation Corps member with us and now with CBF, did was upload 600 photos from reefs all around Chesapeake Bay on this interactive map. So you can go click on 600 locations to see what the reefs look like. Next slide. And then we have some of our greatest hits videos of a lot of the different important species that we've seen on the reefs that you can watch as well, like this one. So thanks for the opportunity to share some of what we're doing and try to learn about oyster reefs, and look forward to discussion and questions later.
That was very informative. And, you know, it tells a really cool story. And I think a lot of times with data, that's sometimes where, you know, there's an opportunity of using pictures and video like that really to convey it. So amazing. All right, next we have Willy Reay, who's going to be speaking to us about shellfish aquaculture industry and emerging estuarine observing systems, and he's from Vince.
Everything working? I'm going to use my notes up here because I have trouble seeing. So first, I want to thank Scott for teeing this up. I think it's going to be appropriate for the discussion we have. I'm going to briefly talk about the way we're moving observing systems and how we can support decision-making in the Chesapeake Bay region. And what I'm talking about here is going to be some work that colleagues at VIMS are doing, and these are folks where we share samples, where we have conversations in the hall, but there's a lot more capacity sitting down at VIMS, but I'll be touching a little bit on that. So we all know the importance of bivalve aquaculture in Virginia, and that was strategic. I mean, we've been actively growing that industry out, and core to that is going to be maintaining water quality. I think that goes without saying, but sometimes that's a good reminder as we move forward. So concurrently with the growth of aquaculture has been the impact of HABs. They have been increasing globally, and we're seeing some negative impacts, both to the shellfish industry, to ecosystems, and also to the humans. I'm not only going to stay out of the clean today. Next slide. Yeah, we have to switch over this a little bit. So elements, I just want to throw out some elements that I'm going to briefly talk about today regarding observing systems. Typically, we look at those as being a little bit more water quality, physical, or weather oriented. Now, in order to really address and help decision making, we're going to have to start bringing in some of the other programs, the other studies that are can be a little bit more complex. So what we'll talk a little bit about today, we're going to be looking at high resolution temporal and spatial monitoring water quality. That has to be intimately tied to what we're calling HABs counts and IDs. We've got work going on with the physiology and toxic production. We have finfish and shellfish pathology that helps us out. Actually, that's at the crust of it. Those are the areas of study that are going to be setting the thresholds and be kind of highlighting the issues out there. And then we'll be moving into now and forecasting HABs water quality issues, the water quality in addition to HABs themselves. We'll show you a little bit about satellites. We don't do that at VIMS, but our partners do. And so that's a tool that we use to help guide our research and monitoring. And then it really doesn't matter what we do. We don't really have a data management or transfer. If we cannot get that information out to our decision makers, it's really for naught. Next slide. Okay, so there's challenges here. So causative factors that contribute to HABs timing, distribution, and density are many. And in many cases, some of them are not well understood. So I think essentially what we're saying is I treat each HAB as kind of a unique event. There is, just as you described, you were worried about Vibrio yesterday, and now you have the rains coming in. You know, so each HAB carries its signature as it moves through the season. But some of the main players are going to be the physical water circulation, temperature and salinity plays primarily with some of the species. Wind is extremely important. So some of the things I'm talking about are coming from a monitoring perspective, and I'll show you some images there. Nutrient supply, these are all setups. That's sort of what, you know, kind of setting the stage. The algae species themselves, they have different physiology. Important also is sediment, the cysts that are in the sediment, what causes those to decide to show up one year. You know, that's sort of the seed bed. Introduced species, we know that there's issues with bilge water, those types of things. We don't work with that here, but our folks that study the individual species do. And then there are food web alterations, whether it's DO events, pH-related pH events, those types of things, fouling. So all those play into it. There are many, and I almost thought that was a good way to show it is. I was having lunch when I made that slide. So it is not a simple can of soup. It is the vegetable soup. Okay, each dish is a little different. Next slide. So this is kind of a neat slide that just shows. So when you're in the monitoring game, we have what we pride ourselves in short-term variability, long-term trends. We want to deliver in those areas. And those are two very distinct monitoring programs that we try to blend. So this side gives you a good indication. The image on the right is just from August in the York River. We have historically, every couple of years, we have an algal bloom multi-species dinoflagellate. But that gives you the issue. I kind of put a couple of numbers there. You'll see a little green line, and then you see a little red line, and you'll kind of see, depending where you take your water samples, you'll have totally different results. So this is what we're dealing with. This is also a nightmare when we're trying to quality assure the data, when we start looking at our monitoring programs. But essentially, we're going from a clean environment to what we consider a very large HAB, depending on where you pull your water samples from. It's not just the HABs. Take a look at the dissolved oxygens, take a look at the pHs, water clarity. All of those are associated with that, and those changed over a 24-hour period. We can go from 200% saturation oxygen down to 10 over the day in a harmful algal bloom, or in a bloom itself. I also kind of wanted to give you a little bit idea on the spatial component of that. You can sort of see that little top left figure. As you go around seasons, we start with diatoms, then we move into a variety of dinoflagellates, and then you start seeing them pop up. Different species pop up with different physiology. And so that's just something to keep in mind there, but that's sort of a neat multi-species bloom. To give you an idea, in that figure there, the counts can be as high as 70,000 per ml. Okay, next slide. So I'm going to I'll be a little selfish on this talk and kind of get into our water quality lab. This is the one measurement that is really used heavily in HABs, but it has a lot of issues with it. And our goal is to make chlorophyll a useful parameter to measure. So it is a universal pigment. We see that. It correlates well with what we call eutrophic status. We can accurately measure it to a point. And then we have a number of ways that we can actually, what we're interested in is continuous monitoring. So there are technologies out there. It happens to be fluorescence, and there are issues with fluorescence. So we keep that in mind when we kind of start going through this a little bit. Next slide. Okay, so here are some of the challenges. I think, let me see if I can see them. So we have sensor characteristics. That's something that comes out of the box. It depends what sensor you're using. It has to do with emission and excitation wavelengths to make sure you're looking at the right organism. Let's say green algae is different than green bacteria. Calibration issues, people calibrate them differently. There are better ways than others. Biofouling, you don't need these sensors. Some folks think you throw a sensor out there and you're good to go for the year. Even we have some of the strictest. Our sensors are only out for 2 weeks at a time. There's so much biofouling going on. Then we're coming down to the environmental factors. There's CDOM, or what we call colored dissolved organic matter that can interfere. We have some interference, and I'm going to get rolling here. And then the big one is the physiological and behavioral impacts from the algal cells themselves. That's where, at least my headache is. Those other issues we can address. That's something that we can adjust. We can, through calibrations, through various adjustments, those types of things, we can get a handle on those. We can adjust temperature to a standard temperature, those type of things. But when we get into the algal cells themselves, they have things, they protect themselves from light. So I can get a fluorescence number and it will not match a sample that I'm going to collect right next to it if I take it back to the lab to extract it. So those are issues we have to deal with. And there are ways, and so we're kind of investigating that. Next slide. So this gives you an idea. So this, just by chance, this was what one of the runs we did on New York just earlier in August. The data normally does not look like this. I'm going to be truthful. This happened to be a great run, and it is leveraged a little bit by those high numbers. So the first graph on the left is when we're running our boat with fluorescence, and then with fluorescence, and then we go back to the lab and look at a lab extraction, and we get a good relationship. But look at the slope of that. It's not a 1-to-1, it's a 3-to-1. Okay, so we need to make adjustments. And then I actually, with Dr. Kim Reese, put her counts next to it, and we got some really nice relationships with that. Next slide. So our water quality monitoring program, I want to give a shout out to Maryland. So the things I'm showing you here are being run in Maryland. So we have fixed stations. We have 16 platforms in the Virginia. That's based on a variety of programs. That's the CBIBs that we help maintain. And then there are DEQ and all the other monitoring programs. Next slide. And we also have a dynamic mapper that goes out every month on our river systems. Right now, we do one river for 3 years at a time, but that gives you some high spatial resolution. That's kind of gives you the tracks that we ran on that figure in August to give you an idea of what that would look like. That's over 3,000 data points to give you an idea of the data sets that you can collect. Next slide. Okay, some quick elements that we have at VIMS. In addition to the water quality monitoring program, we coordinate with our other labs and colleagues. We have what we call SPAC that is able to absorb toxins. Typically, you leave that out for 7 to 10 days. You go back and you extract it. It's found in a resin, okay, and that can be looked at. So for the first time, we had sort of a lower Chesapeake Bay survey of toxins, I think about 2 years ago. It's extremely interesting. We have our molecular genetics lab by Dr. Kim Reese with the DNA-based monitoring. With PCR, that's probably the gold standard. That's looking at the DNA, targeting DNA. And actually, they've got that down to be pretty quick. And then we have particle analysis. While we call it particle analysis, we're interested in the algal cells, but they're particles. So we have flow cams that can be benchtop or in situ. Next slide. Shellfish and finfish pathology. I need to give a shout out. So this would be Dr. Carnegie and then Hamish Small. So what's going on there? They're looking at sublethal and lethal effects, and that's going to guide us on what's important, what we're targeting. Everything we're doing here is grow out beds and hatcheries. So it's the full suite from Bellingers up through adults. Next slide. And just want to show you the satellite imagery. This is from our partners at COSS at NOAA. We actually use this when we're planning our monitoring programs as guidance and our approaches when we go out and things like that. So appreciate that. And I think one more, what's the next slide? Dr. Friedrichs, Margie Friedrichs, her lab is now doing nowcasts and forecasts. So they're doing river and bay now in forecasts, and they're looking at temperatures, salinity. They have DO. They're also doing HABs now, and I believe pH. She's working up those. So take a look at that link there. That's fantastic. The idea about the forecast is they're looking 2 to 3 days down the road. So that's what we're excited about. Next slide. Data processing. I just want to give you a quick idea of what that looks like. Just so when you call up and say, hey, it's taking too long to get my data, you were talking about that. We need to make it available. Different types of data come out at a different time, but it runs from minutes to weeks. And I just wanted to give you kind of what I was briefly talking about, that time frame. Next slide. And this is the last one, is data management and delivery. We have two portals that we work with. Our VCOS is our Virginia Estuarine and Coastal Observing System. That has all the EPA data. I need to give a shout out to the long-term EPA data sets that are out there from '84. Those are critical. And then we're also helping manage the portal for the Chesapeake Monitoring Cooperative. There's the link for the buoy system. There's the link to Dr. Friedrich's forecast system. And below that, I put Kim Reese has HABgrams. I think they're more internal to VIMS, but they're so informative that we may need to talk to her about getting those out. And then just a thank you slide for the teams that we work with.
Okay. Awesome.
Yep.
Thank you, Willy. Amazing. It's going to be like the Q panel from Bond. You guys have all the cool tools. It's really interesting, you know, to see, and something to think about maybe for the Q&A section. I think you teed it up, but just thinking about this stuff in the context of climate change and, you know, how what we're measuring is going to change and why. So without further ado, we have Olivia Caretti here from the Oyster Recovery Partnership, and she's going to talk about large-scale monitoring.
Yeah, thanks, Scott. Is my mic working? Okay, great. You can never hear when you're up here. It works. All right, so I'm Olivia Caretti. I'm with Oyster Recovery Partnership. We are a nonprofit in Maryland, but we work on oyster restoration in Chesapeake Bay. That is our goal. So today I'm going to be talking about our large-scale monitoring framework that we apply in Maryland, but this is something that, this framework can be used to think about applying in other places, but also applying for other purposes. This is stuff that we apply for restoration, but this could be useful for thinking about monitoring on harvest areas or aquaculture farms, et cetera. So some of the considerations that I'll mention at the end are things that I think are themes that have already been brought up today, and hopefully, we can discuss moving forward. So go ahead and next slide. I will add that I'm not really going to be talking about any fancy new technologies, but I think this is still valuable, hopefully, to this session. So at ORP and with our partners, we have two main approaches to monitoring. The first is to conduct pre-restoration monitoring, which Ron talked a little bit about earlier, the value of citing areas that are suitable for restoration to make sure that they are actually going to allow oysters to survive and grow. Our other monitoring approach is post-restoration monitoring. So going back after reefs have been restored to identify whether individual reefs have been successfully restored and then whether entire tributaries have been successfully restored. So I just want to emphasize that with both of these approaches, it's really important to develop clear, objective, and measurable success metrics to track progress before restoration occurs. And so that's something that I really want to stress to everybody. Next slide, please. So in Maryland, obviously, we're working in the upper portion of the Chesapeake Bay. And so when I say large-scale restoration, what this really means is the Maryland tributaries that contribute to the 10 Tributaries Initiative. So those would be Harris Creek, the Tredeavon River, the Little Choptank River, which are all on the eastern shore of Maryland in the Choptank River complex, the St. Mary's River, which is in the southwestern portion of the state, and then the Minokan River, which is the southeastern portion of the state. And I also want to acknowledge that this is not something that we are doing alone. This is a large partnership. Our main partners are the NOAA Chesapeake Bay Office, the U.S. Army Corps of Engineers, Maryland DNR. And I also want to emphasize that we do work with Maryland watermen through a collaborative research program to conduct all of this monitoring and leverage their knowledge and their historic knowledge of working on water. Next slide, please. So to give you an idea of the scale of the work that we're doing, to date, we have surveyed over 1,500 acres in Maryland just in these tributaries to identify areas for placing spat on shell. We have restored about 900 acres to date in those 5 tributaries, and we annually monitor greater than 400 acres, and that includes pre-restoration and post-restoration monitoring. And so again, this is specific to these 5 tributaries. However, we are working in other areas in the state, so this is a very large-scale endeavor. Next slide, please. I'm just going to touch on some of our approaches to monitoring here. So for pre-restoration monitoring, we are working with the Maryland Interagency Work Group, which is the partners that I showed on the previous slide, to generate tributary blueprints, which guide our sampling efforts. And so those blueprints are constructed using bathymetric and side scan sonar data, and also historic oyster maps in these tributaries, and then also historic knowledge of where oysters have occurred in the past. And so by the time that we actually go out in the field, we have a really good basis of understanding where we expect oysters to be or where we expect suitable habitat to be. So we're using these to guide our sampling efforts to determine whether the bottom type that's present can support oysters. For post-restoration monitoring, we are returning to reefs after they've been restored 3 and 6 years after that restoration effort. And so this is to get an idea of shorter term success, allow us time to conduct additional restoration if that initial restoration wasn't considered successful. And then again, 6 years later to get an idea of the longer term success of the restoration effort. And so for our post-restoration sampling, I'm sure people in this room have heard about the oyster metrics, but we are really looking at biological metrics to measure whether oyster enhancement has occurred. So this includes looking at oyster density and biomass, the population structure. Are there multiple size classes of oysters present on this reef? That would indicate that there is recruitment occurring and survival and growth into larger size classes. And then we're looking at what the shell budget is on these areas that have been restored. And then our other partners are looking at physical reef characteristics. So the footprint of the reef, has that changed over time? And then has the relief of the reef changed over time? And so to do this work, we are using a combination of sampling with divers and also sampling, again, I mentioned that collaborative waterman research program, using their gear types, which are really efficient at collecting oysters. So we go out with watermen and use their patent on gear to take benthic grabs to get at some of these oyster metrics. And I will emphasize that, you know, there are limitations to all these gear types that we talked about today, but, you know, I think it's really valuable to also consider touching oysters, measuring oysters, and using those data to help supplement some of the other more remote passive monitoring programs. Next slide, please. So to date, we have seen really, really great success in the Maryland portion of the 10 Tributaries Initiative. So this pie chart on the left is just showing the percent of reefs that have met the target oyster metric, which we use as 15 oysters per meter squared. And then the threshold, or sorry, the target is 50, the threshold is 15. And then 1% of the reefs that we've restored to date have not met any of those metrics. So this suggests that, you know, first of all, sorry, it's the last feedback. Okay, that's it. First of all, this restoration program has been really successful, and this has been successful on a large scale, which is what we want to see, which suggests that this process works, where we are going in. Okay, thank you. Sorry about that. Okay, thanks. Sorry, guys. Just want to emphasize that, you know, the process of going out before restoration occurs and actually conducting this monitoring to verify that areas are going to support oysters is really valuable, and then allows for the success of restoration in general. Next slide, please. I touched on this earlier, but, you know, this is specific to oyster restoration. But I think it's also useful to think about a similar framework being applied to for other purposes. So pre-restoration monitoring can be really valuable for generating a baseline of oyster biomass or some snapshot of what the habitat looks like before restoration occurs. And you can use this to compare to those post-restoration surveys in whatever form they take. This is also useful for verifying areas are suitable for potentially aquaculture leases or for you know, enhancing public fishery areas, which is a process that we do in Maryland as well. Post-restoration monitoring can also be useful for verifying oyster biomass. We've heard a few talks today about water quality and how oysters can enhance water quality and reduce nutrients. And so, you know, being able to go out and measure oyster biomass is valuable for estimating the reduction in nutrients. And then we can also use post-restoration monitoring or post-enhancement monitoring to verify that harvest did or did not occur on a lease, an on-bottom lease, or a public fishery area as well. And again, I just want to emphasize that whatever form your monitoring would take would definitely benefit from developing clear, objective, and measurable metrics before an enhancement activity occurs. Next slide. And so lastly, I just threw a few thoughts up here about things that we're considering at ORP with our monitoring program, the future of monitoring in the Chesapeake Bay and beyond, and just things that we need to think about moving forward. So the first is, you know, what are the goals of monitoring? We are conducting monitoring through 6 years after restoration in the large scale tributaries. Do we need to monitor longer? Do we need to monitor shorter? What are the goals, and how can we adjust our monitoring program to address those goals? Obviously, over time, goals change. So just thinking about, you know, what we need to do as a group that's going to provide us more information, like Scott mentioned earlier, about you know, enhancing oyster production. The second thing is, how long do we need to monitor? That's what I just said. What are additional values of monitoring? So Nat touched on, you know, looking at fish biodiversity and other habitat use. We've talked about water quality again earlier. So what can we use this data for to provide us information about these other ecosystem services? And then lastly, kind of the last few bullet points here are just thinking about how can we use monitoring data to identify things like paradigm shifts, detect multiple stressors or site restoration in the face of climate change, and how can we use this data to adapt our restoration and or enhancement framework, or just how we're going to improve oyster production in Chesapeake Bay. So with that, I'll stop there. I give everyone plenty of time. Thank you.
Thank you, guys. That was a great panel. We're trying to manage the time here, so 1:50 we got to cut it off. So we've got a few minutes here for Q&A. We're going to do some questions from the room if there are any, and then also I can take some from online. And we are down to 3 mics, so either I can pass, or I can pass one back. But I think one of the things is if we get something from the room, it'd be good to repeat it so people online can hear. All right. So as far as the room goes, I think so. You first, you guys, right? Yes.
Yes, so it's for Olivia. Just wanted to, you mentioned that the monitoring is supplemental. I want to emphasize that what you're doing, it's the same thing we've been doing now in Virginia, using watermen who are expert of the water. We find the efficiency of the survey gear at 80%, and it's probably the best form. I would say everything else is supplemental. What you're doing is probably the
Yeah.
gold standard.
Thank you. Yes, I kind of tripped over my words there. I would agree. I think that measuring oysters is the first and foremost most useful piece of information. And then I think we can expand on that and complement that process using these other technologies and gear types to provide additional information. So thank you for clarifying that.
Well, I was also saying the gear you're using, that it's the patent times that the watermen are using. That in particular, we know exactly the efficiency of that gear. And so it's really the most accurate way to sample. And I applaud you because a recent study by Mike Wilbert and others showed that the hydraulic gear that's typically used in other surveys is actually around 20% or so, 20 to 30% efficient. That's trouble for that.
Yeah, I think the benefit of just that whole process is just being able to quantify what your bias is or what you're missing when you collect that data is also really important for filling in the picture. Yeah, thanks.
All right. We have someone hanging back with it. Yes, sir.
A question for Matt. Matt, is the equipment that you guys use for the drone survey, is that something that's user friendly enough that private industries could use it, or is it not to that point yet?
So the question posed to Matt here is the drone tech that they're using, is it affordable enough, you're saying?
Yeah, and user friendly.
And user friendly enough for private users?
Yeah, so thanks. It's a great question. And I guess, these are things that could be deployed on drones. We've been deploying them on boats, but sort of by hand. So the camera stuff that we're doing to take photos and videos is, very user friendly. It's a GoPro action camera that a lot of people have. And so that's been very user friendly. The sonar technology is much more labor intensive and more expensive. They're somewhere on the order of about $85,000. So they're, it's not a cheap fish finder. It's a really nice one. So it's sort of, I think that the answer there would depend on the scale you want to use it for. It could be cost efficient if you have a really large scale area that you're surveying and you're using it a lot. And if you only use it a few times, it's probably not worth the cost.
Good answer. Do we have anything online?
Yep, let's see. We have one from Matt. What's the minimum depth that the sonar can be used? From Katie Cole.
The minimum depth, probably, a meter or less. You don't need a lot of water to use it. And then we've deployed it in the way that I showed us using it. We've deployed it on a frame that you can lower down to the bottom, however deep that is. It also, it's restricted over the area that it can see. So it looks out over about 5 meters, about 15 feet. So it's high resolution, but relatively short distance that it covers.
And then the last question online is, I have a question about using the ARIS system from Matt. How are you telling the difference between the habitats? And is there a standard method? What other information are you capturing with ARIS?
Yeah, great, great questions. So we, with the habitat, we're just starting to use it. We got the ARIS this summer. So one of the things that we're doing is, if you point it straight down like a normal fish finder on a boat would be, or a depth sounder, you can see the surface of the bottom really well. And so it's pretty easy to measure the height of the oysters, or you can see if it's really flat, if you're on a flat bottom. When it's pointed out horizontally, we haven't done a really quantitative analysis of that yet, but we have a lot of sonar videos from the same places that we have the camera work done. So we should be able to compare those things. I've looked at a lot of the video, and I can look at the video and tell you if it's sand. You can see individual oysters with the ARIS. It's high enough resolution to do that. And you can see if there's a few clumps of oysters or a lot of large clumps of oysters. So you can, it was probably hard for you to see it in the still images on my slides, but you can see it in high enough resolution to really kind of see what the bottom is looking at it. I mean, we'll be looking at ways to actually collect quantitative data on that in the future.
One more just came in from Maria Herman for Olivia. Can you briefly discuss what are the most common restoration techniques? And do you need to adjust what's being monitored depending on the restoration technique being applied?
Yeah, great question. Thank you. So in Maryland, the most common restoration techniques are deploying spat on shell. As a lot of people have mentioned earlier, Maryland is sort of larval recruitment limited for oysters, so we deploy spat on shell. We also, in certain areas where the bottom's not really suitable for oysters, we deploy a granite base with spat on shell on top. I think Virginia uses this very similar approach, but it's not putting out spat on shell, they're just deploying shell because there's a lot of larvae available in the system down here. And a mix of other substrates. Someone earlier talked about reef balls, some of the engineered structures, concrete rubble, etc. So varies by location, but in Maryland, we're primarily doing spat on shell or a granite base with spat on shell. Can you repeat the second part of the
question? What's being monitored depending on what technique is being applied?
Great question. Okay, so obviously you can't sample granite riprap with patent tongs on waterman's boats, so that's where we apply divers. We have divers go down and excavate material in a quad drag. So we are primarily using those two approaches. Yeah.
Great. I think we probably have time for questions. If there's one more quick one, it can be quick in the room. Johnny?
Yeah, so this is whoever can answer, but the work that's any work that you guys know of that's being done with underwater drone technology, number one. Number two, are either of you looking at biodensity as a whole on reef for applications for the nitrification method?
The question is, number one, underwater drone use, is that being done? And then the second bit, are we measuring density for denitrification studies? And that's for anyone.
You can take the drone.
Sure. So for the drone part of that question anyway, I know Matt Gray has a program at the UMC's Horn Point Lab. I've seen a lot of stuff on their Twitter recently about some of the drone work that they're doing. And I think Ram and Rochelle are doing some with VIMS as well. Those are the ones I'm most familiar with.
Yeah, same. I think those exhaust my knowledge. And then your second part of your question, density for denitrification. There's a lot of work being done out of University of Maryland, Horn Point and VIMS on that work. So I haven't seen anything coming out recently, but there's a lot of that. And then I'm sure you know as well about the Oyster Best Management Practices report that should be coming out in a few months for public review. So there's a lot of interest in measuring oyster biomass or other fouling organisms for denitrification.
Great. Thanks, everybody. Thanks for the great questions. And thanks again to panel two.